right, here we go. We are going to talk about growth and decay, which we talked about last time. But we are going to look at the word problems that have to go with this. I kind of introduced this last time about where we would see exponential functions in real life. We talked about how the increase in a car or a house could be exponential. You see population growth of people, animals, bacteria. Bacteria is definitely going to grow at exponential rate. That's why so many of you have the flu. Interest earned on money in the bank or the stock market. So if you put money into a savings account, it's going to grow slowly, but then eventually it's going to take off. And then on the flip side of that, interest you have to pay on loans is exponential. And then radioactive decay, carbon dating. So just as a review, here are the two different equations for exponential growth and exponential decay. We talked mainly about this equation last time, the y equals ab to the x. Okay, and we talked about what each one of those letters meant. So remember we said that a was our y-intercept, and that b, that's going to tell us if it is growth or decay. Remember, if it's greater than 1, then it is going to be growth. If it is less than 1 but greater than 0, then it is going to be decay. The equation that we're going to be more concerned with today is going to be this y equals a times 1 plus r to the x power. But remember, everything in that parentheses, that's still your b. So if that adds up to be greater than 1, it's growth. If it adds up to be less than 1, then it is decay. Okay, and this graph is just showing you that that was exponential growth. And we looked at the domain and the range of that last time, and then remember we also looked at what an asymptote was. Okay, we won't really be looking at asymptotes today, or really domain and range, so please make sure that you understood that from last time. All right, so exponential decay, same equation, y equals ab to the x power, but here your b is going to be less than 1 but greater than 0, so it could be 0.25 or 1/4 or 1/2 or 1/9 or whatever. Anything greater than 0 but less than 1. But the equation that we're going to be dealing with more today is the y equals a times 1 minus r to the x power. Okay, just as a review, we talked about this last time. Remember, we're looking at this b term to decide if it is growth or decay. So here in this first one, 2, that's greater than 1, so that would be growth. The second one, 3 over 2, okay, I have to think about, yeah, that's a fraction, but let's think about what that number is. That's 1.5, which is greater than 1. So that one's also growth. That's kind of a tricky one because you're used to, when you see a fraction, you're used to thinking that that's decay. Okay, now 1/2, that is less than 1, so that would be decay. This next one, 1/4, that's also less than 1, so that is decay. 2 to the 3, that's the number we're concerned about here. That is bigger than 1, so that is growth. And then this next one, 0.2, that's less than 1. So that one is decay. So we talked about that last time. If you were absent last time, you probably have no idea what I'm talking about. Okay, the exponential growth model, this is what we're going to be dealing with today. And this is still y equals ab to the x. It's just that b is broken down into 1 plus r. So it's important that you know what each one of those letters stand for because we're going to have to be plugging numbers in for those. Okay, so that a, that is going to be our initial amount. Okay, remember, we talked about that last time, how that a is our y-intercept, and that a means, or that y-intercept means initial, that's the start. So that's our initial amount. Okay, I also introduced that r, that stands for the rate. Okay, and then just remember, when they give you that rate, they're going to give it to you as a percent. So you're going to need to change the percent to a decimal. Okay, so for the rate, you're going to need to change the percent to a decimal. We'll see that on these examples. Okay, that 1 plus r, remember that's our B. That's going to be our growth rate. Okay, so basically you're taking your rate and you're adding it to 1. That's our growth rate. And T is exactly what you probably know it is time. Whether that's years or days or months. All right, so here we go with this first problem. All right, we're talking about an investment. You put $250, $250 in a savings account that earns 4% annual interest compounded yearly. You do not make any deposits or withdrawals. How much will your investment be worth in 10 years? All right, so here we go. So we're going to have Y, that's our total amount at the end of this, equals, we need our initial amount, we need the A, and it looks like we're starting out with $250, so $250. And then 1 plus our rate is 4%, but you got to change that to a decimal. That's 0.04. Okay, and then we need to the T power, so we have to find our time, which is 10 years. Okay, now I know this looks like it's difficult, but we're just going to plug this in our calculator. Now you need to be aware that I could also write this as 250 times 1.04 to the 10th power with that 1 plus 0.04 being added together. But you don't need to do it that way to type it in the calculator. Just know, if you were to see this as a multiple choice, this second option could be the answer choice. Okay, now we're going to plug this in our calculator. All right, so go to your, not your Y equals, not there. Okay, and we're going to type our equation in. So we've got 250, 1 plus 0.04, or you can just type in 1.04. I just don't want to accidentally add those wrong, so I'm going to type in the original, and then to the 10th power. And there we go. There's the amount of money that we would have after 10 years, earning 4% annual interest compounded yearly. Okay, I'm going to round that 2 decimal places because we're talking about money. And so here Y is going to equal $370.06. Okay, so these are actually pretty easy. You just have to know where to plug the numbers in. Okay, here we go. Now we're talking about cell phones. So in 1985, there were 285 cell phone subscribers in the small town of Centerville. The number of subscribers increased by 75% per year after, that's important, after 1985. How many cell phone subscribers were in Centerville in 1994? Okay, and this says don't consider a fractional part of a person. That's going to make sense whenever we get our final answer. All right, so here we go. Now this is telling us it's growth, but if it weren't to tell us it's growth, you would need to see this word increase and realize I need to use the growth model. All right, so here we go. We've got Y equals our initial amount, which is 285. Okay, and then we have 1 plus our rate. Now it says it's 75%, but as a decimal, that's 0.75. Okay, and our time here. Now our time is not 1994. It says that it's happening per year after 1985. So how many years after 1985 is 1994? Well, that's 9 years later. Now we have our equation. So I'm going to go back. I'm going to type this in to calculate it. So we've got 285. You can either add 1 and 0.75 or just type it in like it is. So 1 plus 0.75 to the 9th power. And we get 43,871. And I know that it's 0.98, so you think that you should round up. But we don't actually have 43,872 yet. So in this case, we've seen this before. But in this case, I would have to round down. So $43,871. Okay, here we go. Number 1. Consuela and Matthew paid $215,000 for their house in Grapevine. If the house appreciates, that's a big word, appreciates, at a constant rate of 3% each year, the value V of the house after n years can be represented by the function V equals P times 1.03 to the n power. P is the price, which is the most reasonable value of their house after 5 years. Now this is actually, it's already filled in the rate for you. It's already said that this 1.03 is 1 plus your rate, which was 0.03. So it's already simplified that for you. So now you just have to plug everything else in. So you have P, which is the starting value. So 215,000. Now you need to know that that word appreciates means to grow. Okay, it's increasing. Okay, so I have 215,000 times 1.03. Okay, and the time is 5 years. We're going to type that in our calculator. So we've got 215 times 1.03 to the 5th power. There we go. So 200. Oh, I typed an extra 0 in on my 215,000. All right, so it's 24,920. Okay, I'm going to do this again because I typed something in wrong. So 215,000 times 1.03 to the 5th power. There we go. So 249,240. In this one, it looks like in the answer choices, it's going to, it is rounding up. So that would be answer choice B. Okay, I'm going to give you a little bit, and I want you to work number 2 on your own. I'll go ahead and read it. So one of Texas's towns had a population of 2,000 10 years ago. If the population has grown exponentially at a rate, so it's grown exponentially at a rate of 20% each year, what is its most reasonable population now? Okay, 10 years from now. So y'all go ahead and plug that into the equation. Then we'll go over it. All right, here we go. So the starting was 2,000. Then you got 1 plus, your rate here would be 0.2. And then it says 10 years ago, one of Texas towns, the population 10 years ago, the population has grown exponentially each year. Okay, so to the 10th power. And that should get you answer choice B. Okay, let's look at this next one. All right, the amount of money in Edda's savings account has increased over time according to the function shown in the graph. She deposits the same amount from every paycheck, and she has done so for several years. Which of the following is true about the effect of regular deposits into an account with compound interest? So there is still interest. Even though she's depositing the same amount, which we would think that's linear, there's still interest being accrued, so that's not going to be linear. So A says her money increases to a certain point and then stops growing. Well, this graph, it looks like it doesn't ever start growing, so that's out. B, her money increases according to an exponential function. Okay, that could be an option. Her money increases according to a linear function. Well, that graph clearly is not a straight line, it's a curve. So that's not it. And her money increases in an unpredictable way. Okay, this curve right here is made because it's predictable. This is why different companies will use this to figure out what's going to happen in the future. It's an exponential curve. So it is B. Okay, let's talk about decay. So we talked about stuff growing. Let's talk about when different situations decrease. All right, so this is all the same. The A is the initial amount. Okay, R is the rate. Again, that's going to be a percent, but you have to change to a decimal. 1 minus R is your decay rate, and T is your time. Okay, so here we go. Population of a city decreased. So if you were to see this word problem, you would know you need to use the decay model. So it decreased from 1995 to 2003, from 1995 to 2003, by 1.5% annually. In 1995, there were about 357,000 people living in the city. Write a function, okay, so that means write an equation. Write an equation that models the city's population since 1995. Then find out the population in 2003. Okay, so here we go. So we've got y equals, what's our start, our initial, so that's 357,000. Okay, 1 minus, since we're decreasing, and our rate here is 1.5%, which means I need to move that decimal over twice. So it's going to be 1 minus 0.015. And then it's since 1985. Well, 1985 to 2003, that's 8 years. All right, I'll let y'all go ahead and type that in your calculator. Go ahead and type that in. Okay, when you do, you should get 316,342 people. Okay, moving on. All right, each year the local country club sponsors a tennis tournament. Play starts with 128 participants. During each round, half of the players are eliminated. How many players remain after 5 rounds? Okay, so notice in this problem, they don't give you a percent. They don't give you a rate. Okay, but they do tell us that half of the players are eliminated, and half, that would be 50% of the people are eliminated. Okay, so we're going to use that as our rate. So we have y equals our start, which is 128. It's decreasing because the draw is getting smaller, so we've got 1 minus. Okay, 50% as a decimal would be 0.5, and then there's 5 rounds. So we'll go ahead and type that in our calculator. So after 5 rounds, we have 4 players left. Okay, here we go. Interest can work for or against you. Investments like cars and electronics usually depreciate. Okay, we saw appreciate earlier. Depreciate, that means decreases. So it depreciates with time. The value of a $25,000 car depreciates by approximately 11% per year. How much would the car be worth after 5 years? Okay, and it gives us the formula again. So we've got y equals the starting value, which is 25,000, 1 minus our rate, which is 0.11, and then to the 5th power. Okay, so go ahead and type that in. Figure out how much the car would be worth after 5 years. And you should get 13,960. All right, we've got one more slide to go. All right, the population of a town T years after the town's largest employer went bankrupt can be modeled with the equation P of T equals 27,500 times 0.85 to the T power. Okay, I don't like this first question, so we're going to skip it, but I do want to answer the rest of these. So number 2, what is the population's rate of decrease? Okay, so let's think about that. Now this is confusing right at first because our decay rate is right here. Okay, our decay rate is 0.85. But you have to think that that number was made from doing 1 minus our R. Okay, so if that's the case, 1 minus R is equal to 0.85, which means our original rate was 0.15. Kind of a tricky question. So you've got 15% was the rate. What was the initial? So you know the initial is that A value, that number in front. So that's 27,500. Okay, and we are not going to answer number 4. Okay, so in summary, exponential growth and decay are mathematical changes. The rate of change continues to either increase or decrease as time passes. In exponential growth, the rate of change increases over time, okay, and the rate of change becomes faster. Okay, this slide is going to be important for one of your homework questions. Okay, because you have to think, if it's growing, it grows slow, and then it starts to grow really, really fast. In exponential decay, the rate of change decreases over time, and the rate of change becomes slower as time passes. So think about driving a car off the lot. Okay, it's going to decrease really quickly, but then it's going to slow down. Since the rate of change is not constant, the same, remember constant, that means linear. Exponential is not linear. So since the rate of change is not linear or constant across the entire graph, these functions are not straight lines. And what are they? They are curves. So there we go. Okay, when you're done, turn this in to the sub, and he will give you your homework, and you should finish your homework before you get done with class. So make sure you finish that, and we will go over it next time.